Okay, 2 times square root of 3 divided by 5 times square root of 3 minus 4. This one is, I wonder if I can, this might get messy. I wonder if I should copy and paste it. 2 times the square root of 3 divided by, was it 5 times the square root of 3 minus 4? I think that's what it was. Uh-oh. 2 times square root of 3. Okay, we're good. Now, here we go. It's illegal to express a fraction when you have a radical in the bottom. So right now, that's illegal. I can't simplify anything. I can't pull anything out. I can't simplify any fractions. So I need to somehow legalize this radical on the bottom. And you're going to use a conjugate. Because this is a binomial, there's two terms, I'm going to multiply it, always multiply by 1, that's the trick. But your 1 is going to be kind of an interesting one. It needs to be a binomial that when you multiply these two suckers together, all you're left with is a whole number, an integer. So this will always work. A conjugate, you just kind of copy and paste what you've got there, but you're going to change the sign. You're going to change it to a +4 instead of a -4, and you just created a difference of squares. So 5 times the square root of 3 plus 4 on top and bottom. Now the bottom, here's what's way cool. Anytime you multiply a difference of squares, there's a lot of canceling that happens. So if I multiply these two guys together, 5 times 5 is 25. Square root of 3 times square root of 3 is square root of 9. Now I got to multiply this. 5 times 4 is 20 times the square root of 3. Now a -4 needs to be multiplied to both. So -4 times 5 is a -20 square roots of 3. And a -4 times 4 is a -16. Okay, that is all my denominator. Okay, this is what I love right here. This is the difference of squares. That's what happens. These two terms will negate each other. They zero out. They're opposites. So when you add them up, there's nothing. And this is what is awesome. Number 2, you created a perfect square. What is the square root of 9? It's 3. So you really have 25 times 3, which is 75. 75 take away 16. So you are at, on the bottom now, you're at 59, which is a nice whole number, a nice integer. So that's a way cool trick. Now you just have to multiply the tops. You need to distribute and times both of these guys by 2 square roots of 3. So 2 square roots of 3 times 5 square roots of 3 is 10 square roots of 9, and 2 square roots of 3 times 4 is 8 square roots of 3. And you can clean this up right here. So 10 times the square root of 9 is really 10 times the 3. So it's a 30 plus 8 square roots of 3, and on bottom you have got 59. Done. Okay, let's maybe copy and paste this next one. 15. I'll bet we got room in here. I'll bet this one will fit. Okay, this is a multiplication problem. On the outside you got a 2, and on the outside of here you got a 1. You times those two together to get 2. Underneath the radicals you times these guys together. So 15 times 200, or 20, 15 times 20 is 300. And then you got to times your x's. X cubed times x is x squared. Alright. Move number 2. Always do the prime factors of any number under a radical. So I'm going to go to 103, I'm going to go to 10 and 10, 5 and 2, 5 and 2. So now I'm going to write 2 on the outside. Underneath, what do I have? I've got 5 squared times 2 squared times 3 times x squared. And now it's a square root, so let's pull things out in sets of 2. So on the outside I've got a 2. Anything I pull outside, I'm going to multiply it. So 5s, I've got 2 of them, so I'm going to pull out a set of 5s. I'm going to pull out a set of 2s. And I think I messed up here. My x is right here. That's a mess up. It should not be x squared. It should be x. Let's see. Eraser. Should be x to the 3 plus 1. So it really should be x to the 4th. So I messed up. I gotta change this to a 4. Alright, I pulled my 5s out, pulled my 2s out. There's nothing left over. 3, there's not enough, so he stays underneath. X's, I've got 4 of them. I can pull them out in sets of 2. I'm gonna pull out 2 of them. So a 2 times a 5 times a 2 is a 20x squared on the outside. Underneath, just the square root of 3. Okay, computation. This is going to be the last one. It's a fraction. Now fractions are pretty cool because you can simplify them just like you would a normal fraction. So here's the rules. 2 is on the outside. It only plays with what's on the outside, which is a 1. So what's underneath plays together. So this 3 and this 18 play together. 3 and 18 is always going to be 1 and 6. Always, always, always. Now your x's, if you've got 2 x's on top and you've got 3 x's on bottom, this x is going to cancel that x, this x is going to cancel that. So both of those x's on top zero out. And on bottom I'm only going to have 1 x. Okay, now your y's, 1 y on top is going to eliminate 1 y on bottom, so on bottom I'm going to have y squared. Okay, now look at your top. Your numerator is awesome because square root of 1 is just 1. So on top I've just got 2 times 1. On bottom, can I pull anything out? 6 is pretty small. There's not going to be enough to pull anything out. So 6x, but I do have enough y's I can pull some out. And we're 99% done. The only thing that's wrong is it's illegal. You cannot have ever in a fraction a radical on the bottom. So this one's quite a bit easier than the one we just did. You're just going to times it by 1, but your 1 is going to be what the problem is. This is illegal, so you're going to copy and paste this, the number and the letter, everything underneath there. So on top you're going to have 2 times the square root of 6x. On bottom you're going to have y times the square root of 36x squared. And what you just created is a perfect square. So this is going to all come out of the radical. So on top you got 2 times square root of 6x. On bottom we've got a y times a 6 times an x. Because square root of 36 is 6, square root of x squared is x. So we've got 2 times square root of 6x over 6xy. 2 6 is going to change to 1/3. Done. Okay. What would a number line look like if it only had the natural numbers? Well, it would not look like a line at all. You'd have a dot right here for 1, a dot for 2. You would have nothing in between, so you cannot connect those with a line. You'd have a dot for 3, you'd have a dot for 4, whoops, a dot for 5, etc., etc. So it would not be a line at all, it would just be points. What would it look like if it only contained the integers? It would look just like this. So I'm gonna copy paste all this stuff, but then it would also go the other way. You'd have a dot for 0, you'd have a dot for -1, a dot for -2. So it really wouldn't be a line, it would just be points, because there's nothing in between these points. From 0 to -1 is empty. There is no space, there's nothing. Now if we put the rationals in there, it is getting pretty dang close to a number line. Here's 0, here is 1, here is 2, here's a -1, here's a -2, and it's going to go forever. But it's not going to be complete. So for example, I know this. I know that this only contains the rationals, so I know, for example, square root of 2 is like 1.41 blah blah blah. So in between 1 and 2, I'm gonna have to erase a chunk. Somewhere near 1.41, your number line would be empty. So if you were driving down the road, you drive off a cliff, you drive into a huge pothole, because square root of 2 is an irrational number. And if this line only contained rationals, so right here, there would be a break in your number line. There would be an empty spot. And pi is like 3.1415 blah blah. So between, here's 3 and here's 4. Between 3 and 4, there would be another pitfall. Pretty close to 3. There'd be another gap in your number line. So your number line is almost complete, but every once in a while there's going to be a chunk taken out of it. Okay, the last one. What would it look like if it only contained the rationals or the irrationals? It would look more like these first couple. So you would have a spot here for square root of 2. You'd have a spot here for square root of 3. Have a spot here for pi. You have a spot here for square root of 5. So there'd only be spots here and there. So the closest to a complete number line is the one that has all the rationals. Okay, the closest natural number to 100 is either 1 below or 1 above. And that is the exact same for the wholes, because wholes are also naturals and integers are naturals. So copy paste all 3 answers. But these final 2 get a little funky. What is the closest rational number to 100? If I'm approaching 100, so if I'm at 99 and I'm going to 100, between 99 and 100, there's going to be a decimal like 99.9999 with trillions and billions and zillions of these nines. Infinity of them, an infinite amount. And if I'm coming from 101 and I'm going to 100, there's going to be a decimal like 100.000001 with a bunch of zeros. But the answer is, there really is not one. There's not one unique number, because no matter what you choose, I can always find one smaller. Same for here. There's really not one. Kind of a weird idea, but no matter what you find, I can always find one smaller. Okay, these are good ones. Square root of 24 lies between what 2 integers? Square root of 24, I know this. I know that 4 squared equals 16, and I know that 5 squared equals 25. So I know the square root of 16 is a 4. I know the square root of 25 is a 5. So square root of 24 is somewhere between these 2 guys right here. So on the number line, it's between a 4 and a 5. Square root of 95, so this is what I want to see on your test. Square root of 95, I know that 9 squared is 81. I know that 10 squared is 100. So, square root of 81 is 9. Square root of 100 is 10. 95 is between 81 and 100, so it's got to be between 9 and 10, some kind of a decimal. Okay, now the cube root of negative 28. Now you just start guessing, because you don't know cubes or 6 or 8s or 7s roots at all. So you choose a number. I'm going to choose a negative number. I'm going to choose a negative 3. So negative 3 cubed on the calculator, don't forget to put negative 3 in parentheses, is a negative 27. So I'm just a little bit off. So the next choice is going to be a negative 4. Negative 4 cubed is a negative 64. So here we go. I know negative 28 is between 27 and 64. So my answer is between a negative 3 and a negative 4. We're going to run out of time, so I want to do this guy right here. 8th root of negative 29. There is no solution, because any number times itself 8 times is always positive. So they want you to multiply some number 8 times and end up at negative 29, but that's impossible, because no matter what number you choose, and if you multiply it 8 times, your answer is always going to be positive. Okay, maybe one more. Let's do this. 7th root of negative 65. So you're going to choose a number. I'm going to choose a negative 2. So a negative 2 times itself 7 times on the calculator. Overshot it. Negative 128. And I know a negative 1 times itself 7 times is a negative 1. So it's between these two numbers. It's between a negative 1 and a negative 2. And this is the last. So from your problems of the week, this has probably been the best one so far. What number is in the ones digit when you simplify the following expressions? Okay, 4 to the 100th. 4 to the 1 is a 4. We're going to find patterns. 4 squared is 16. 4 cubed is 64. 4 to the 4th. What's 4 to the 4th? 256. And I think we're done. I totally see a pattern. The ones digit, all you care about is this very last digit. So it looks like when you multiply by 4 over and over and over and over again, your ones digit bounces back from 4 to 6 to 4 to 6 to 4 to 6 to 4 to 6. So the question is, 4 to the 100th, does it end on a 4 or does it end on a 6? And it ends on a 6 because the 6th ends on every even exponent and the 4 ends on every odd exponent. So I'll leave, let's do maybe one more. Let's do 8 to the 32nd. Okay, 8 to the 1 ends in an 8. 8 squared is 64. 8 cubed is 512. No pattern yet. 8 to the 4th, 4096. Still no pattern. 8 to the 5th is 3276. Okay, I think I got it. So 8 to the 6th, just to be sure. 8 to the 6th, blah blah blah, ends in 4. So here's my pattern. 8, 4, 2, 6. 8, 4, 2, 6. So here we go. When my exponent is 1, my answer is 8. When my exponent is 2, my answer is 4. When my exponent is 3, ends in a 2. When my exponent is 4, it ends in a 6. And when my exponent is a 5. It ends in an 8 when my exponent is a 6. It ends in a 4, 5, 6, 7, 8, 9, 10, 11, 12. I gotta stop at 32. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. You can count like that. And that's a pretty slick way, and you know you're going to end up exactly on the 6. So it's going to end up on the 6. Or you can say there's 4 numbers in the pattern. So it's going to repeat every 4th time. So 32, how many groups of 4 are there? 32 divided by 4. That's going to cycle through exactly 8 times with no remainders. So on the 8th time, it's going to end up evenly with no remainders on the 6. That is it. Good luck.